we can combine all of the gas laws that we talked about in the last set of videos into one equation called the ideal gas law, where the pressure times the volume is going to be equal to the number of moles times T, the temperature. Now, all of this is there's a constant that's involved, and we call this constant capital R. Capital R is called the ideal gas constant. This actually has a value of 0.0821 liter atmosphere over K mole. Okay, so PV equals nRT. This is called the ideal gas law. Okay, now the reason why we keep saying this phrase ideal gas and not just calling it gas, there's actually a thing that we're trying to make a point here with what an ideal gas is. So let's define an ideal gas. An ideal gas is a hypothetical gas whose pressure, volume, temperature relationship can be completely accounted for by the ideal gas law. So this is a hypothetical gas whose pressure, volume, temperature relationship can be completely accounted for by the ideal gas law. Okay, so yeah, this is a hypothetical gas that the pressure, volume, temperature relationship is completely accounted for. Now, keep in mind that this ideal gas law, what this equation is, it's a mathematical model. At the end of the day, it's just a mathematical model that shows how pressure and volume and relationship are intertwined to each other. All right, so if that's what an ideal gas is, it's a hypothetical gas, when does the ideal gas law actually model real gases? Well, it turns out that the perfect temperature and pressure for the ideal gas law to work, it's going to be at 273 K and at 1 atm. Now, in chemistry, we give a special name to this temperature and pressure. We call it standard temperature and pressure. Or STP. Now, here's the cool thing. Let's say you're at 273 K and 1 atmosphere, so you're at standard temperature and pressure now. If you have N is equal to 1 mole, okay, so let's assume you have 1 mole of a gas. 1 mole occupies exactly 22.4 liters. So that's pretty cool. If you know that the temperature is going to be 273 K, pressure is 1 atmosphere, and you know that N is equal to 1, then V is going to be equal to 22.4 liters. All right, so I'll tell you what, let's try just a straightforward ideal gas law calculation. Let's just try one out, and then we'll talk about some other things that come up with the ideal gas law. So let's try this problem out. Here's our problem. Calculate the volume in liters of a gas occupied by 2.12 moles of nitric oxide at 6.54 atmospheres and 76 degrees Celsius. All right, so the way I go about doing one of these is we know that the ideal gas law says this, PV equals nRT. So I'm going to write that equation at the top so that way I know I've got to make sure I've got all these variables. So what I'm going to do is on the left-hand side, let's list out the information that we know. So for the pressure, we're told that the pressure is 6.54 atmospheres. Okay, so I'm going to write 6.54 atm. Volume, that's what we're looking for. Okay, so volume, I'm going to put a question mark. That's the unit that we're looking for. and it's defining it that we need to be in liters. Okay. N, number of moles. We're told that we have 2.12 moles. So let's put that in. Okay. T, the temperature, we're told that we're at 76 degrees Celsius. Now, this is a problem because we're going to have to convert this to K at some point. Okay, so I'm going to make that little note there. Finally, the only letter that we haven't accounted for is R. So let me write that R term in. So that's going to be 0.0821 liter atmosphere over K mole. All right, so now we have to rearrange the ideal gas law in such a way that we can solve for our missing variable. In this case, we're going to solve for V. So if we divide both sides by P, look at what happens. So if we divide both sides by P, the P's are going to cancel out, so we get this, that V is going to be equal to nRT over P. And so that's going to be the form of the equation that we're going to solve for. All right, so now that we've got our letters, we've got the equation we need, what we're going to do, the last thing we have to do before we start popping in our stuff, we've got to figure out this temperature. So in order to convert the temperature from Celsius to Kelvin, we have to add 273 K. So let's do that. So if we add 273 K to that temperature, we're going to get the temperature in Kelvin. So 76 plus 273 gives us 349 Kelvin. All right, so cool. We got our numbers. All the units are matching up. So now we can just pop in our values. So let me write the equation one more time. V equals nRT over P. Okay, so let's pop it in. So N is going to be 2.12 mole. R, that's the universal gas constant, so I'm going to write 0.0821 liter atmosphere over K mole. Okay, I'm going to multiply this by our temperature, which is 349 K, and then divide all of this by the pressure, which is going to be 6.54 atmospheres. All right, now what's really cool about this is this constant is that, look, you've got all the units that you need for that problem. So when you start canceling out the units, moles cancel out with moles, Kelvin cancels out with Kelvin, ATM, when we do the division, cancels out with ATM, so the only unit that you're left with is liters. Okay, so this is going to be 2.12 times 0.0821 times 349 divided by 6.54. The final answer is going to be 9.29 liters. And there it is. So pretty much at the heart of every single ideal gas law, this is the calculation. Eventually, this is it. This is the heart of everything. So the only difference is that you may have to do a little bit of work to get these letters over here, the P, the V, the N, and the T. You may have to do a little bit of work. Sometimes you may have to do a stoichiometry problem to get N. But at the end of the day, that's how this works. Now, we can use the ideal gas law and help us find the molar mass, calculate the molar mass, or calculate the density of a gas. So to do this, we're going to have to manipulate the equation just a little bit. Okay, so keep in mind that if we're going to calculate density is going to be mass over volume. Okay, so that's going to be our equation. We need to get mass over volume. Now, the only thing that we have close to that in the ideal gas law is that we've got a volume term, but instead of mass, we've got N, the number of moles. All right, so how do we calculate the number of moles? In order to calculate the number of moles, we have to take the mass, okay, which I'm going to use lowercase m for, divided by the molecular weight. And if you take these two, that gives you the number of moles. Okay, so let me write MW. Okay, so what we need to do is take our ideal gas law and we need to rearrange it so that way we get N over V. Okay, All right, so we need to get N on top. We also need to get V on the bottom. So what I need to do is what I'm going to do is divide both sides by RT, so that way N's by itself. Okay, so let me start with the ideal gas law. PV equals nRT. I'm going to divide both sides by RT. Okay, so that way that cancels out. We get an N by itself. What I'm also going to do then in my second step is then divide both sides by V. So that way now we got an expression that says this: N over V, which is as close as we can get to density, is equal to P over RT. All right. Now, the way that we calculated N was that we take the mass divided by the molecular weight. That gives us N. So what we're going to do is replace N in the ideal gas law with M, the mass, divided by the molecular weight. So if I rewrite that equation and make that substitution, here's what I get. The mass divided by the molecular weight, okay, divided by V is equal to P over RT. All right. Now, here's where it gets a little tricky, and you're like, oh my God, how can this get even worse? Now, if I ignore, I need to simplify this a little bit before I start doing anything else, because I've got a complex fraction. Now, if I try to multiply and get this all in one fraction, I can rewrite this so that way the volume times the molecular weight, that will be on the denominator, mass will be on the top. So let's rewrite that. So the mass divided by the molecular weight times the volume is going to be equal to pressure over RT. Now, M over V, this part here, if we were to ignore the molecular weight, which we can't, but if we did, that would be our density term. So we're getting closer. So now, if I was able to multiply this whole thing on the left by the molecular weight, then that would be out of the equation on the left-hand side. But we'd also have to do the same thing on the right-hand side, multiply the right-hand side by the molecular weight. All right. So if I try that, let's see how that works. You're going to get M over V, this is, by the way, density. Okay. This would be equal to the pressure times the molecular weight divided by RT. And there it is. There it is. We have an expression to help us calculate the density of a gas. Now, keep in mind that the molecular weight, if we were to solve for the molecular weight, that would be like something like this, where it would be D, the density, times RT over the pressure. Okay. Now, a lot of times, so we could, if you know the density, you could solve for the molecular weight. Now, sometimes it's a lot easier to solve the ideal gas law, get N from the ideal gas law, okay? And then once you have the number of moles, you hopefully you would know the number of grams from the equation or the problem that you've got. You would just take the number of grams divided by N, and that's going to give you the molecular weight as well. All right, so that being said, let's try another problem out. So here's our problem. A gaseous compound with 78.14% boron and 21.86% hydrogen. At 27 degrees Celsius, 74.3 milliliters of the gas exerted a pressure of 1.12 atmospheres. If the mass of the gas was 0.0934 grams, what is its molecular weight? So we got a lot of stuff going on here. All right, so we're told that we have a compound that contains boron and hydrogen. And we're told information about this gas. All right, so let's try to suss out what we've got. Now, we could figure out the empirical formula and get from the empirical formula its molecular formula. The only difference is we don't have the molar mass, which that can make things a little bit easier to get the molecular formula. We're going to need that. So in order to get the molecular weight, in order for us to figure out the molecular formula and use these percentages, we're going to have to use the ideal gas law. So let's write out what we got for the ideal gas law. We know pressure is going to be 1.12 atmospheres. Okay. Volume, we're told, is 74.3 milliliters, or 0.0743 liters. Okay, so we need to make sure that the units are matching. All right, so we got that. Temperature, we're told 27 degrees Celsius. We need to convert that to Kelvin, so that's going to be 300 Kelvin when you add 273 to it. All right. Now, we have pressure, we have volume, we have temperature. We also know R because that's the universal gas constant. The only letter that we're really missing in this whole thing is N. Okay, so here's what we're going to do. We're going to solve the ideal gas law for N. We're going to get the number of moles, and then once we get the number of moles, once we figure that out, then what we can do is since we know the mass, okay, we'll divide it by the number of moles, and that's going to give you molecular weight. And then that's when we can apply all the percentages to that and then help us get the molecular formula. So it's going to be a 3-step process. So the first step, we figure out N. Second step, we get the molecular weight. And then the third step, we apply the percentages and get the molecular formula. All right. So let's start this out. Let's figure out what N is. So here's the ideal gas law, PV equals nRT. We're solving for N this time, so we're going to divide both sides by RT. All right, so that way we get that N is equal to PV over RT. All right, so there it is. All right, so now we've got our letters, we've got our variables, we got the values, the units are matching up. So let's plug in what we've got. So we know that the pressure is going to be 1.12 atmospheres. Okay. The volume is going to be 0.0743 liters divided by R, which is 0.0821 liter atmosphere over K mole. And then T is going to be 300 K. All right, so K's cancel out. And then once we do the fancy divisions, the liters and the atmospheres will cancel out. So the only unit that we're left with is moles. We're good. All right, so when we take 1.12 times 0.0743 times divided by the product of 0.0821 times 300, that number I get is going to come out to be something like 3.38 times 10 to the minus third moles. All right. So now that we know what N is, if we take, to get to the second part, if we take the mass, because in the mass we're told, the mass in the problem was 0.0934 grams. Okay, so if we take 0.0934 grams, and let me rewrite that, 0.09, okay, divided by the number of moles that we just calculated, so 3.38 times 10 to the minus third moles, and do this math, 0.0934 divided by 3.38 times 10 to the minus third, the number I get is 27.6 grams per mole. So that's our molar mass. All right, so now that we have our molecular formula, what we could do is take our percentages, okay, because we know that the compound is going to contain 78.14% boron. Let's figure out of this number, this 27.6, out of this number, how much of that number is boron and how much is hydrogen. So let's try this out. So for the boron part, okay, you know the mass, 27.6 grams per mole, and I multiply that by the percentage. In the problem, we were told it was 78.14. So converting that to a decimal point, 7814, that number I get is about 21.6 grams. So that's how many grams of boron we have. Now for the hydrogen, we'll do the same thing, 27.6 grams per mole times the percentage, and that was 21.86 or 0.2186%. That number comes up to be 6.03. Now, we have to convert these from grams to moles. And if we convert boron from grams to moles, it should come out to be 2 moles of boron. And for the hydrogen, it should come out to be about 6 moles of hydrogen. So therefore, the answer to this, the molecular formula, should be B2H6. And there it is. So that was a little tougher. This was a 3-stepper. So step 1, we had to use the ideal gas law and solve for N. Step 2, based on the problem, figure out the molecular weight. Step 3, determine the molecular formula based on the percentages given to us and the molecular weight that we calculated. All right, let's try one more problem. The ideal gas law could also be used in order to solve a stoichiometry problem as well. So let's talk about how this could work. So here's a problem. You've got a 2.14 liter sample of hydrogen chloride gas at 2.61 atmospheres and 28 degrees Celsius. It's completely dissolved in 6.68 milliliters of water to form hydrochloric acid solution. Calculate the molarity of the acid solution. Assume no change in the volume. All right, so here, let's write out what we know. We know that the pressure is at 2.61 atmospheres. Okay, the temperature is 28 degrees Celsius. So that should be, if we convert that to Kelvin, 301 Kelvin. Because we're converting by adding 273 to it, you're good. All right, now the volume, we're told 2 different volumes. So the gas has a volume of 2.14 liters, but we're also told that we have 668 milliliters of water. All right, so the only letter that we're missing, and we know R, by the way, the only letter that we're missing again is N, the number of moles. Now, once we know the number of moles, we now know the volume of the solution. N divided by the volume is going to give you molarity, and there we go. That's how we're going to get the answer. So the first step, we solve for N. Second step, we solve for molarity. All right, so here we go. Let's get the ideal gas law, PV equals nRT. We're going to divide both sides by RT, so that way it ends by itself. So we get N is equal to PV equals over RT. All right, we got our letters, we got our numbers. Let's pop everything in. So the pressure is going to be 2.61 atmospheres. V is going to be 2.14 liters divided by R, 0.0821 liter atmosphere over K mole. And then T is going to be 301 K. All right, now the canceling out the letters that we've got, we're going to be left with moles, so that's the unit. So this is going to be 2.61 times 2.14 divided by the product of 301 times 0.0821. And so that number should come out to be 0.226 moles of HCl. Now, since we got the number of moles of HCl, that HCl is being bubbled into 668 milliliters of water. So for the second part, if we take the 0.226 moles of HCl and divide it by 668 milliliters, or if we convert that to liters, 0.668 liters, that should give us molarity, and that molarity should come out to be 0.338 liters. Or molar solution. So 0.338 molar solution. And there it is. All right, and so those are the types of problems that we can do with the ideal gas law.